Okay, we're going to, as I mentioned, kind of wrap up the last little part of chapter 4. Then I'm going to, time permitting, do a little previewing of some stuff that will hopefully help you with lab next week. And then we'll be done, hopefully. Or whatever questions you have, I'll be happy to answer sort of after that. All right, so we last left off, I think, when we were all together with electron configuration. And remember that when you write electron configuration, there's really two things that you need to know to really pretty much do any electron configuration. That is, s orbitals could hold a maximum of 2 electrons. P subshell could hold a maximum of 6. D subshell maximum of 10, and F subshell maximum of 14 electrons. And you could recreate the order at which they go into the atom by just remembering on the first energy level, there's only S's. On the second energy level, there's P's. On the third energy level, there are D's. And on the fourth energy level, there are F's. And then you basically just fill in the numbers underneath each of those. And you'll basically just recreated the order that you need with the appropriate letter there. And it does go to about 7. So that would be 3P, 4P, 5P, 6P, 7P, and D, 3D, 4D, 5D, 6D, and 5F. And remember that we always start here and roll our way through. Again, you don't have to fill up anybody completely and so forth as we go through. So for example, if we were to look at, say, I don't know, we'll do zinc, which is number 30 on the periodic table. That means it has 30 electrons because it is neutral. And it has 30 protons. So once again, we would start here, and that would then be 1s2. We would then roll to our next one coming through here as we come this way and then back through. That would then be 2s2. We would then come back and roll into here. That is the P subshell, which means we could put 6 in there. That's going to be 2p6. Remember that you can count up the top numbers, and I'll tell you how many electrons you got in there. That is 8 and 10. So we definitely need to continue on. That's going to be to here, which would be 3s2. Again, coming back to here would be 3p6. That's 18. So we still need to go. That's now going to go to 4s. So remember, the 4s is less than the 3d. So that would be 4s2. And that is like 20 right there, I believe. So coming through here, we're going to go to 3D next. And that would be 3D. It kind of ran into there, 10 in that case. So I'll just go down here. It's 3D10 at the end. And that should be 30 at that point, and that would be the electron configuration. Remember, we could back up on the periodic table to the one that comes before it, which in this case would be argon. And you could do sort of the shorthand there. It would be 4s2, 3d10, if I didn't screw that up there. And that would get us 18, 20, and 30. Any questions on electron configuration? So those are really the two important things. The nice thing is you really can recreate the order for you, and you pretty much could write any electron configuration you need. Remember, there were 2 exceptions that we talked about, which was chromium and copper. Again, copper having 1 extra electron in the D, 1 less in the S, and the same thing with chromium. It has 1 less electron in the S and 1 more in the D. Any questions on how to write electron configuration? So to finish up sort of the chapter 4 part, we're going to talk really about periodic trends and some of those things that are important. First thing we're talking about is valence electrons. Valence electrons are the outermost electrons in an atom. So if we look at somebody like lithium, which is number 3, and wrote the electron configuration for it, 1s2, 2s1. Remember that the first number here represents the energy level. So in this case, on the second energy level, lithium has how many electrons? It has 1, yeah? So it has 1 electron on the second energy level. And that would be the highest in this case, and that would be its valence electrons. These are lower in energy, these two, and these are sometimes referred to as core electrons. Now, valence electrons are the ones that are involved in bonding because, frankly, they're furthest away from the nucleus and they're not held as tightly. And because they are the furthest away from the nucleus, when two atoms come together, they're really the first ones to say hello to each other because they're on the outside, basically. So they're involved in all kinds of bonding that we'll talk about. And you can write the electron configuration to figure out the valence electrons. This is nitrogen's. How many valence electrons will nitrogen have? It is 5. These are both on the second energy level, right? So they both have 2s in front of them. So this would be its 5 valence electrons. This would be its core electrons there. And again, the valence electrons are the ones involved in bonding. So one way that you can figure out the number of valence electrons is simply to write the electron configuration. The much easier way is the number of valence electrons equals the group number. So everybody in group 1 has 1 valence electron. Everybody in group 2 has 2 valence electrons. Everybody in group 3 has 3, obviously 4, 5, 6, 7, and 8. 4, 5, 6, 7, and 8. These are all the transition metals there. Good news is usually you don't have to worry too much about transition metals in terms of bonding and valence electrons. In terms of transition metals, as we might have talked about, when transition metals lose electrons, they actually do lose the s electrons first. So a lot of people consider those the valence electrons, the 2 for the transition metals. Some will say they could have more because after they lose the 2, they could then go into the d orbitals and take some electrons out of there. But most of the time, people will probably hang out with 2 in terms of how many valence electrons transition metals have, but everybody else, it's equal to the group number, which makes it fairly easy to remember. And that's why when we look at lithium, which is group 1, that is its valence electron. And we look at nitrogen, which is group 5, that is the 5 valence electrons that we see. So a much easier way to figure out the valence electrons is equal to the group number. So really the valence electrons are the highest energy electrons. So when you look at an electron configuration, I'll just kind of write 1s2, 2s2, 2p4, for example, right? This is the first energy level, which is the lowest. That's on the second, which is the highest here, and that's also on the second, which is the highest as well. So in the case when looking at this, you would want to look at the first number here, that's the largest. And since there's 2 electrons in that guy's orbital and 4 in that subshell, this guy should have 6 valence electrons. Yeah, so if you did 1s2, 2s2, 3s1, this would have how many valence electrons? It would just be the 1, which is that one. That, by the way, is 2, 4, and 5, right? And on the periodic table, number 5 is boron, right? Did I count that right? 1s2, 2s2. I skipped the whole 2p. I'm sorry. Let's try that again. 2p6, 3s1. Get the right configuration on there. I'm like, I feel like I missed somebody there. So that would be the 1 valence electron, but if we count it up, that's actually 11, which would be sodium, which is group 1 on the periodic table in that case. So fluorine is group 7, so it has 7 valence electrons. Chlorine also group 7 would have 7, and carbon has 4, so it had 4 valence electrons. Much easier in writing electron configuration, and usually you're going to use this when you're drawing things like Lewis structures, which we're going to talk about after naming. And obviously, you don't want to be writing electron configuration to draw Lewis structure, so you can just go to the periodic table to do those things. So we're going to talk a little bit about some periodic trends, which tells us what we see here. And basically, in terms of metals, which are on the left-hand side of the periodic table, nonmetals, which are on the upper right of the periodic table, we typically will find the most reactive nonmetals up here, upper right of the periodic table. And the most reactive metals are actually down here on the lower left of the periodic table. And that's because of some of the periodic trends we're going to talk about here in just a second. And they all lead to what we sort of know happens with metals and nonmetals, which is metals typically will lose electrons. Nonmetals will typically gain electrons, like we were talking about with naming. And what really leads that to happen are what we're going to talk about here, which are some of these periodic trends. The first sort of periodic trend we want to talk about is what is referred to as ionization energy. Ionization energy is the energy that is needed to remove an electron from an atom in a gas phase. The higher the ionization energy, the harder it is to remove an electron. The lower the ionization energy, the much easier it is to remove an electron. The general trend on the periodic table for ionization energy, which is on the next slide, but we'll just look at it here, it increases as you go up and to the right on the periodic table, and it decreases as you go down. That means as you go up and to the right on the periodic table, it gets much harder to remove electrons because it takes a lot more energy to do so. And as you go left and down on the periodic table, not that hard to remove it. It doesn't take a lot of energy to sort of do that. By the way, this is a reaction that shows the electron coming off on the right-hand side. It's like it's being given off and becoming positively charged. We associate ionization energy with cations, which are positively charged ions, because those are guys that obviously would lose electrons. Electrons actually come off one at a time. They just don't all really pop off at once. So it actually happens in a multiple step sort of process. So speaking of our friend lithium here that we just wrote the electron configuration for, 1s2, 2s1, what first would happen in this particular case is lithium would then lose one electron, and it would pop off over there on the right-hand side of the arrow to indicate that it's being lost. And the energy required to do that is what is sometimes referred to as the first ionization energy. What would then theoretically happen next is lithium with a +1 charge would then lose another electron and become a +2 charge. And that would be the second ionization energy. Do you think it is easier to remove the first electron or like the second or third electron? Which one's easiest to move? The first one is much easier to remove. What happens to the size of the neutral atom once you lose an electron? Does it get larger or smaller? It does get smaller as you lose electrons. It does start to shrink. And the ionization energy here would be much smaller than it is here. In fact, in the case of lithium, as we just learned, lithium is group number 1, which means it always makes what type of charge? +1, which means this is the only thing that happens in the case of lithium. And it is why it only will make a +1 charge, because lithium, which is group 1, has how many valence electrons? 1, and it would be this guy right here. So once lithium loses that valence electron and it wants to try to lose another one, we're now into the core electrons, which are held a lot tighter because they're closer to the nucleus. And even more so because it lost an electron, it just moved everybody closer to the nucleus, which is going to hold everybody a lot tighter. In fact, it's probably like a 12-fold difference in energy required to do so, and it just does not happen. So that's why something like lithium will only make a +1 charge, because anything further than that is not energy efficient to happen, and you won't be able to rip out that electron from those core electrons. That's also why something like calcium, which is group 2, has 2 valence electrons. You could take off the first electron in calcium, gets much harder to take off the second electron, like 4-fold difference. And then if you try to rip off a third electron from calcium, you're into those core electrons. It's already lost 2 electrons and become much, much smaller, and it will not basically come off, and it won't happen. So ionization energy, general trend, increases up to the right, decreases as you go down. Another important trend is atomic size. It also decreases as you go up and to the right, and it actually gets larger as you go left and down. It decreases in size as you go to the right, because as you go to the right on the periodic table, you get a lot more protons, which means the positive charge in the nucleus is much higher. Much higher positive charge in the nucleus is going to bring everybody in a lot closer to start with. And that's going to give it a much smaller overall size. And as we go to the left and down, they have a lot less protons, but more electrons. So they're really spread out in terms of their size. There's a couple of other really important sort of trends to go along with this. One is what is referred to as electron affinity. And if you have an affinity for something, that usually means you like it. So that is the energy change when an atom gains an electron. And the general trend on the periodic table is as you go up and to the right, it's not perfect, but as you go up and to the right, it increases. And as you go down and to the left, it decreases. A trend that kind of goes with that is what is referred to as electronegativity. And that's the ability of an atom to bring electrons towards itself. That also on the periodic table increases as you go up and to the right, with fluorine being the most electronegative element you could have, and decreases as you go down. Fluorine is the most electronegative element you could have because it is far up and to the right you could go before you go one more group over, which is the noble gases, and they're chemically inert. They ain't looking to do anything. They're just hanging out. So fluorine would be our most reactive one. So putting together all these trends that we just talked about in terms of the periodic table, as we go up and to the right, our ionization energy increases. As we go down and to the left there, it decreases. The size of the atom gets smaller as you go up and to the right, bless you. And it increases as you go down and to the left. Our electron affinity increases, EA, electron affinity, increases as you go up and to the right, decreases as you go down. And lastly, our electronegativity increases as you go to the right and decreases as you go down. What all these trends have in common are when you take all these trends in common, when you look at the periodic table in the upper right, that is where we have our nonmetals. And on the upper right of the periodic table, you have things that are very small, which means to start out with, their electrons are super close to the nucleus. That means they have very high ionization energy, which means good luck trying to remove an electron. They have very high electron affinity, which means they like to gain electrons. And they have very high electronegativity, which means not only do they like to hang on to their electrons, but they like to bring electrons towards themselves. And all those trends together is why nonmetals will typically gain electrons and become negatively charged. As we go to the left of the periodic table, that is where we have our metals. And what we have as we go to the left is atoms that are much bigger, which means the outer electrons are further away from the nucleus and not held as tightly. That means that you have very low ionization energy, which means it doesn't take a lot of convincing to let an electron leave. They have very low electron affinity, which means they are not looking to gain electrons. And they have low electronegativity, which means they're not interested in bringing any electrons to themselves. All of those trends together means metals typically are like, go ahead, take my electrons, please. I don't really care. They are the ones that will typically lose electrons and become positively charged. So these trends explain why nonmetals typically are the ones that always gain electrons, and metals are always the ones that basically will lose electrons. Any questions on any of those trends there? So last thing we're going to talk about here in this chapter is some Lewis dot symbols. And Lewis dot symbols are also just generically called sometimes electron dot symbols. And basically they are the symbol, and we use a dot to represent one valence electron. So there really is kind of no rule other than you shouldn't put more than 2 dots per side. That means there's 4 sides and 2 dots. That's a grand total of how many electrons? 8. And the whole purpose of bonding, ionic bonding, covalent bonding, is for everybody to end up with the exact same electron configuration as those in the periodic table that have 8 valence electrons. Who has 8 valence electrons in the periodic table? Group number 8, which is the noble gases. So the noble gases is what everybody's trying to achieve in terms of bonding. That's what makes them really stable. Noble gases are chemically inert, they're stable, they're good to go. Everybody else through bonding, either transferring electrons, sharing electrons, the ultimate goal is for them to end up with the same electron configuration as a noble gas. They're not going to change into a noble gas, but in terms of their electrons, they will be the same as a noble gas. So we represent bonding using electron dot symbols. In an electron dot symbol, the only electrons that are shown are the valence electrons. So all these elements have more electrons, but just the valence electrons are shown because they are the only ones that are involved in bonding. So it does represent a symbol like sodium and a dot because it has 1 valence electron. Obviously, sodium has 11 total electrons, but 1 dot to represent it. Calcium has 2 valence electrons, so we'd represent it like so. So here is a picture of some Lewis dot symbols: 1 valence electron, 2 valence electron, 3, 4, 5, 6, 7, 8. A note that in group 8, helium is part of group 8, but it only has 2 dots on its Lewis structure. Why is that? Or Lewis dot symbol. Why is that? How many electrons does helium have total? 2, so it can't have 8. And so everybody else in group 8 will have 8, but helium has only 2, so they're both its valence electrons. Also, why in bonding, another really important thing to keep in mind, hydrogen, which comes before helium, only needs to get to helium to be happy and stable, which means that's why when we draw hydrogen in bonding, never ever more than 2 electrons, because it only needs to get to helium to be stable. Everybody else needs to get to 8, basically, except for hydrogen in most cases. Any questions on that there? All right. Any questions on chapter 4? That really does wrap up chapter 4. All good? Okay. So with the holiday, the exam coming up and all that good stuff, I do want to touch upon some chemical reactions and equations and balancing them here to kind of preview it. So hopefully they'll help you with some of your lab coming up on next week. So let's talk a little bit about that. So in our book, I think that's chapter 7, I think is where this is in our book. So a little bit about chemical reactions here. There is really 3 reasons why a chemical reaction will take place. One reason is the formation of a solid, which is sometimes referred to as a precipitate, abbreviated PPT. The other real reason why a reaction takes place is the formation of water. And the third reason why a reaction takes place is actually a transfer of electrons. You pretty much, no matter what the reaction you're looking at, can pretty much know that that's one of the 3 things happening. Either you made a solid, you made water, or there were some electrons being transferred. Ultimately, that is what is going on in all reactions. So let's talk about a chemical reaction. A chemical reaction is a chemical change, and we represent a chemical reaction with a chemical equation. And a chemical equation basically has 2 parts. there are what are referred to as the reactants, which is your starting material. And on the other side of the arrow are what we refer to as the products, which is basically what was formed. So left-hand side reactants, right-hand side products, that's what's going on in a reaction. Now, sometimes we do see some other symbols written in. Sometimes we will see an S written next to a formula. We will see an L written next to a formula. We'll see a G written next to a formula, or we may see an AQ written next to a formula. S is a solid. That means that guy is in the solid form. L is liquid. G is gas. AQ is what is referred to as an aqueous environment. It's basically a water environment. Now, you may be wondering, what is the difference between, say, aqueous and liquid? There is a difference. For example, if you took water, that would be what is considered a pure liquid. If you took water and added to it some solid sodium chloride or salt, the salt will dissolve in the water, right? And when it comes together, you will end up with a sodium chloride solution, which typically gets the aqueous symbol. So aqueous is usually representative of a solution. And usually when you make a solution, you take something like water, put something in it, dissolve it, and you got a nice homogeneous mixture. Everything looks the same throughout type of solution. Now, so those are very common. Other things that we sometimes see written on top of the arrow is a catalyst. And a catalyst is not a reactant. It is not a product. And it does not get used up. In the reaction. Really, a catalyst is there to speed up a reaction. So usually a catalyst is used to speed up a reaction. They can be something that's a solid. So maybe over the arrow, you may have something like platinum written there or some type of metal. Sometimes people will write H+, which implies that it's an acid being used as a catalyst. So sometimes you'll see things on top of the arrows. Any questions on a chemical equation here? Now, whenever we use a chemical equation, it should always be balanced. And the conservation of mass is the idea behind that. When we have a chemical reaction, the absolutely only thing that's happening is all the reactants basically are breaking their bonds, and all those elements recombine on the other side as new compounds, new substances. We never ever lose elements along the way in a chemical reaction. So there's always a conservation of, if you started with 4 carbons, you should end with 4 carbons. They may be in different things, but you should still have the same 4 carbons that you started with. So it is really important when we have an equation that we always balance the equation. And when we balance the equation, the only thing that we change is the coefficients. And those are the numbers that come in front of the elements, or sorry, in front of the formulas in a chemical equation. We never change any of the subscripts, the little numbers. We don't put big numbers in between letters. It's always just the number in front. The ultimate goal is to make sure that you have the same number of elements on both sides. Now, there's 2 things that you have to be sure of. When you have a completely balanced equation, all the coefficients need to be whole numbers. So you cannot have anything other than whole numbers when it's all said and done. And they need to be the simplest set of whole numbers. So what I mean by that is, if you have an equation, let's just say you were able to balance this equation using these numbers in front, each of these numbers, and we'll just pretend it's balanced. The problem with this is I could do what with each of those numbers? Divide them by 2 and still end up with a whole number. So this technically wouldn't be the properly balanced equation. You would need to go through and divide everybody by 2 And then you would have the properly balanced equation. So that's what it means by the lowest, simplest whole number ratio that's present. All right, so what is the approach for balancing equations? Let's take a look at some here. Let's say we have N2 plus H2 makes some NH3. So I personally am a big fan of tables. So if you make a table, kind of see what you got going on, it kind of helps you direct where you should balance the equation. So we have kind of the reactant side on the left, we have the product side on the right, and basically we just have nitrogen and hydrogen as our elements that are involved. So we just first want to take an accounting of, what we got going on. On the left-hand side, we have 2 nitrogens, which is that number. Yeah. On the right-hand side, how many nitrogens do we have? We have just 1. Yeah, there's no number next to it. Remember, the number on the bottom goes to the guy to the left. And if there's nothing written, it's assumed to be 1. So we actually just have 1 nitrogen in this case. Left-hand side, we have 2 hydrogens. Right-hand side, we have 3 hydrogens. Yeah. So this is sort of where we're starting. So this sometimes helps us. And usually you want to attack kind of what's the easiest just to fix. So clearly we could easily fix the nitrogens by putting what in front of NH3 on the right? We could put a 2 in front of it. Yeah. So if we put a 2 in front of it, that 2 gets multiplied to every element that is behind it. That means now we have how many nitrogens on the right? 2. How many hydrogens do we now have? 6. 2 times 3 is 6. So very common when we go to balance an equation, we kind of fix one thing, but pretty much screw up something else. And that's a very common sort of process. Not a problem, because now we could go to the left-hand side, and to fix it, the hydrogen on the left, we should put what in front of it? A 3. That would give me still the 2 nitrogens from here. And once again, 3 times 2 would give me 6 hydrogens. This would be the properly balanced equation at that point. Again, the only thing that I changed was the numbers that came in front, nothing else other than that. Question on that there. All right, so why don't you try one here? Let me try to make one up. I'm going to try my best here. We'll go with, let's go with C2H6 plus O2, CO2 plus some water. All right, see what you come up with. Hang on one second. Let me see. Actually, let me do a different one here. I'm going to give you one a little bit easier first. We'll go with 3, and let's go with 8, I think. I'm going to say I'm hoping so. I'm just kind of going off the top of my head here. Let's see here. So let's try this one here. Let's do 3, and let's do 8. All right, let's do that one. I think it will be a little bit better here for the second one out of the gate. All right. So again, only change the numbers come in front, make a table, see what you got going on. All right, let's take a look and see. So again, I'm going to make a table here, reactant and products, and it's going to list all my elements: carbon, hydrogen, oxygen. Left-hand side, we are starting with 3 carbons. Right-hand side, we have 1 here. Left-hand side, we have 8 hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens. Right-hand side, how many oxygens do we have? We do have 3. 2 there and 1 there would make 3. All right, so we can see we don't have a lot going on in terms of things balanced. So probably the really easiest one to fix would be carbon. We could fix carbon by simply putting a 3 in front of it. And when I do that, I now will have this 3 distributed to everybody. So I now will have 3 carbons. I still will have 2 hydrogens here. And now my oxygen is up to how much? 7. We have 6 in the first one and 1 more back over here, which would give us 7. All right, so we fixed the carbons. We still want to look for what would be the easiest. Oxygen would not be the easiest because it's kind of all over the place. It's in a lot of things. So we might want to save that for the end. But we can fix the hydrogen really easily by putting a 4, right, in front of the hydrogen on the right. And if we do that, once again, this 4 goes to everybody behind it. That gives us still 3 carbons. 4 times 2 here is 8 hydrogens. Oxygen, we now got up to how much? We got 6 in the first one and 4 in the second one, which 6 and 4 is 10. Any questions up to that point? At this point, it should be really simple to fix. We definitely don't want to touch anything on the right-hand side, right? Because we'll just undo what we just did. We could go to the left-hand side, and to get 10 oxygens, I should put 1 in front of O2. Should put a 5, right? 5 times 2 is 10, right? So that will give me my 10 oxygens. We still have my 8 hydrogens and my 3 carbons, and this would be the properly balanced equation there. Yeah. Question on that one there. All right, let's try one more maybe here. I remember what I was going to try. Let's try this. All right, give that a go, see what you come up with here. So the parentheses is pretty much where kind of like where we laid up and talking about naming. So there are things called polyatomic ions. And whenever you have polyatomic ions and you have more than one of them, you do need to put parentheses around them. And the number on the bottom indicates how many you have. So in terms of balancing, if you want to kind of keep track of everything, if you do have parentheses, technically speaking, the number on the outside gets multiplied to everybody on the inside. If you actually put a number in front, it also gets multiplied to everybody as well. So it kind of works both ways. Now, since we talked a little bit here about the polyatomic ions, and we'll talk officially about it, but if you recognize some of these polyatomic ions and you actually have them in the actual formats and they look the same. And what I mean is, even if you don't know this is a polyatomic ion, that NO3 and that NO3 is pretty much like the same thing on both sides. A lot of times it's much easier to keep those things together than going like individually each element, because there's a lot of, as you said, parentheses to multiply in, then you got to multiply out and all those kind of things. So if you ever have anything that is a polyatomic ion like that, that you have them looking exactly the same on both sides, that's actually the best place to start in terms of balancing it. And you would want to keep those together. So you could even still make a table if you like, where you have your reactant side, you have your product side, you have your lead, you have your sodium, you have your chlorine. But in this case, I'm going to keep that polyatomic ion. It's just like a whole unit, so I don't have to kind of multiply in and that type of stuff. And that would actually be the place where you would want to start in this case. And this is how easy it is if you do keep them together. How many of these NO3 units do I have on the left? I have 2. On the right-hand side, how many do I have? 1. So to fix that, I could simply just put a 2 in front of the sodium. And that now gives me 2 of those NO3 units on the right. And it also did change the sodium, right? Now on the right-hand side, I have how many sodiums? And on the left-hand side, I have 1. So that actually tells you where you should go next. So I could fix the sodium by going to the left-hand side and putting a 2. That fixes my sodium, but now gives me how many of the Cls? 2, which is good because on the right-hand side, how many do I have? Oh, that's all good. And lead on the left I have, and on the right I have. We're done. So whenever you do run across this, and we'll do some more examples, obviously, when we talk about it, but if you do have those polyatomic ions, I would highly recommend not breaking them apart and doing element by element. A lot more room for error where you got to kind of multiply in. Obviously, you could not do that on the top one because there was nothing like that. So you do need to go element by element. And in most cases, you do need to do that. But definitely, if you see those, keep them together and start with those. And usually everything will sort of fall into place like it just did there if you kind of keep them together and balance them like that way. Any questions on that there? Now, we won't get into it right now, but you can balance an equation using a fraction if you need to. But you do need to clear the fraction, so it is possible to need to balance it. The last thing I want to talk about, which should also help you, which I think is in that lab as well, coming up next week, is ways to classify different types of reactions. So let's just talk about the different classifications and how you could recognize them, and then I'll be quiet, I think. All right, so ways to classify a reaction. And there are many ways you could classify a reaction. And you could even classify the same reaction in many ways. I know it says wise. I meant to say ways, but it's all right. See if you're paying attention, you know. That's why I was not an English major. Ways, is that better? I think that's good. Okay. So the first type of reaction that we have is one that's referred to as a synthesis, or sometimes a combination reaction. And much like the name implies, it's basically putting things together. So comboing it or synthesizing it. So the general form of that is like A plus B makes A and B. So like two things make one thing. So if you kind of see that in an equation, that's definitely a synthesis or combination reaction. So for example here, if we had H2 plus O2, gives us H2O, which we need to do some balancing to be correct there. That is two things make one thing. That is definitely a synthesis or combination reaction. A little bit of magnesium plus some oxygen. Magnesium oxide, as you burn that, maybe you do that in this class still. I don't know. This sets off the fire alarm. It's good. But this is two things that make one thing. That's your classic synthesis or combination sort of reaction. The direct opposite of that reaction is what is known as a decomposition reaction. And in a decomposition reaction, you start with one thing and you kind of break it apart into two or more things. So really the opposite, if you run an electrical current over water, it will break apart into hydrogen gas and oxygen gas. You could do it with like a 9-volt battery. It works pretty well. But that is one thing that makes two things. So that's a decomposition reaction. If you took something like carbonic acid, doesn't hang around a very long time, breaks apart into water and CO2 gas. One thing makes two things is a decomposition reaction. So they're really opposites of each other. Synthesis puts it together. Decomposition is where you start with one thing and break it apart into many things. Any question on those two types of reactions there? You don't get which one? So this is a decomposition reaction. You're basically starting with one thing, which is water, and it breaks apart into multiple things. And that's basically what a decomposition reaction. You're basically just breaking it apart. Same thing here. This is one thing, which is carbonic acid. It breaks apart into two things. So it's basically you start with one thing and it just decomposes and breaks apart into multiple things. That is what a decomposition reaction is. A synthesis reaction is the opposite. You start with multiple things and you make one thing. So it's kind of the opposite of it. So synthesis puts it together, decomposition basically breaks it apart. Question? Yeah. In terms of balancing? Yeah, so if we I don't know which one we're talking about, but this reaction or that reaction. So we put a 2 here that gives us 4 hydrogens on the left, right? And that has 4 hydrogens on the right here. And this 2 gets multiplied over here. That's 2 oxygens. And that is 2 oxygens down here. So it's balanced in that case. Not sure I balanced this one, but maybe I did. I did balance. This one's actually is balanced on there. They have the same number of elements on each side. So another classification of a reaction is one that's referred to as a single replacement reaction, or sometimes people call it a displacement reaction or exchange. In a single replacement reaction, what happens is you have one thing by itself, like a piece of metal, no charge, or a non-metal that has no charge. You then have an ionic compound. And what happens is if this was a metal, it will come in and kick out the positive guy and will make a new ionic compound. And this guy will come out by itself. So a very common example a lot of people do in lab is they take a piece of zinc. So that's like a metal, no charge. They add some hydrochloric acid to it. Hydrochloric acid is basically a positive and negative guy. Zinc doesn't have a charge here, but when zinc gets a charge, it's going to be a positive charge. So it will always come in and kick out the positive guy. When it does, hydrogen comes out by itself. And when hydrogen is by itself, it's H2, which is a gas. You'll see a bunch of bubbles sort of happen when you do this. And then the zinc will now get a charge at this point, and it will have a +2 charge, and it will hook up with the chlorine that needs 2 of them to balance it out. And this is an example of a double displacement reaction, a little balancing happening there. So the way you can recognize a double displacement reaction, you usually just have one thing by itself, nothing else attached to it, just one element. And then you have an ionic compound, and that usually will lead you to what's known as a single replacement reaction. So this is like one guy by itself, an ionic compound, and that's usually what you will should end up there. The other type of reaction is what is known as a double displacement reaction. And in a double displacement reaction, you actually start with 2 ionic compounds. And always when you have 2 ionic compounds, a positive and negative guy, what happens is the 2 positive guys, they switch partners. So on the other side, what happens is the A, which is positive, will hook up with the D, which is negative, and the C, which is positive, will hook up with the B, which is negative, and actually make 2 ionic compounds on the right-hand side. Sometimes these ionic compounds on the right-hand side makes a solid. It's a very common thing. And sometimes it will make water, which is the 2 reasons why a reaction takes place. So for example, if you took silver nitrate, which you will probably do, and you add some, say, sodium chloride to it, that is a positive negative guy. That's a positive negative guy. These 2 guys are going to switch places, and you will end up with silver chloride and sodium nitrate. This is a positive negative guy, positive negative guy. And by the way, this guy makes a solid, which is sometimes referred to as a precipitation reaction. And that is what a double displacement looks like. So how you recognize the difference between them and double displacement, you have 2 ionic compounds you're starting with, pretty much going to be a double displacement. You can stop looking at that point. If you have just 1 ionic compound and somebody by themselves, a metal or a non-metal, is going to be a single replacement reaction. And lastly, combustion reaction is the last one. I think that might be in there. And in a combustion reaction, most people look at the organic combustion reaction. An organic guy is carbon, hydrogens, and oxygens plus O2, CO2 plus water. If you see any of these 3 things together, it's a combustion reaction. So what happens when you light your Bunsen burner? Yeah, that's a combustion reaction. Methane comes out, and you get heat usually, and flame is basically what you get on those type of things. A more generic definition of a combustion reaction is frankly any reaction that has O2 on the left-hand side of the arrow. So a really, really generic definition of combustion is that's pretty much all you need, is just that guy there on the left-hand side of the arrow is considered a combustion reaction. So these are some different ways that you could classify a reaction. In some cases, you could classify the same reaction in multiple ways, but this is hopefully just a preview of it. And